Hey, good morning, guys. It's super early this morning. I don't think I'll be very funny or exciting, but we will do some fun calculus. We're going to talk about a different method for solving differential equations. The method is called separation of variables. We talked about, or you did one method on your homework last night or whatever, where you pretty much just had an equation solved for dy dx and you integrated both sides. So when you're doing separation of variables, you're going to have a form that looks like this. It's going to be dy dx or y prime, we'll talk about that in just a second, is equal to some function of x times some function of y. Um, so what happens is that if you can get all the y's on one side with the dy, all the x's on one side with the dx, and you can integrate both sides and get rid of the dy dx, and then take your what you have left after you integrate and solve it for y. So here's a couple hints. So sometimes the differential equation you're given is not written in terms of dy dx. If it's not written in terms of dy dx, if it's written in terms of y prime, that would probably be one of the first things I would do is to switch it over. So let's say this, if the, oh, sorry, if the dE, the differential equation, is written using y prime, replace y prime with dy dx. This will make things a little simpler for you. Alright, so what you want to do is you want to take, and sometimes they're nice and they will solve the equation, or they'll give you the dE solved for y prime or dy dx, and then sometimes they won't. So kind of the first thing I would start by doing is to take my function and get all the y's and the dy on one side and all the x's and the dx on the other. So let's say first, of course, after you replace y prime with dy dx, you want to move all y's on the side dy, and then there we go, move all the x's and the dx to the other side. So after you do that, you get all the x's and the dx on one side, all the y's and the dy on the other. Then you're going to, so I guess we'll say second, you're going to integrate both sides. And then simplify. This usually involves solving for y, but in some cases where you have a y squared, sometimes we'll just leave it, or y to a power. Sometimes we'll just leave the left-hand side as y squared or y to whatever power you have. So let's look at some examples. And I'm just going to work a few examples for you, and then y'all will work some in class. So they give us dy dx is equal to 2x over y. This is a pretty simple example. Kind of start with the simple stuff. So I want to move my y's over here with my dy, and then I want to take this dx, and you're just going to multiply both sides by dx and move the dx over with the 2x. So let's do that. So we're going to multiply both sides by y, so we get y times dy. And then we're going to multiply both sides by dx, so we get 2x dx. And now if we integrate both sides, it looks like something that you're pretty similar to used to seeing. So we're going to integrate this, and we get y dy. The integral of that is equal to integral of 2x dx. And now we're just going to integrate. So the integral of y dy, you know, is just 1/2 y squared. And we're not going to put a c on this side because we're going to put a c on the other side. It really doesn't matter which side you put the c on. We'll talk about c in just a minute. And then this becomes 2 times 1/2 x squared. And that I usually put the c on the side with the x. And now we are just going to simplify a little bit. So let's see. The 2 and the 1/2 will cancel. And then I'm going to move the 1/2 over to the other side. So we get y squared is equal to 2x squared plus 2c. Now, when you're manipulating constants, this c over here that you have, what we're going to do, the way that your textbook does it, is they initially call it C1, which I think is just a little confusing. I'm just going to call it C, but what we're going to do is, since we don't know what the constant c is, and it kind of represents any constant that's out there, 2 times that constant still just represents any constant that's out there. So 2c, we're just going to write as c. Anytime you have a constant that's multiplied by a number, a lot of times you'll see e raised to the c power. We're just going to rewrite that as c, because it really doesn't matter. You know, it's just any constant to the c power. Or any a number times c, just another constant. So we get y squared is equal to 2x squared plus c. And then we can solve for y if we want. We can leave it like this. It really doesn't matter. It kind of depends on if it's multiple choice question, how the answer is given to you. If we take the square root of both sides, we do have to put a plus minus in front. So I'm just going to leave it the way it is. That's pretty good. So this would be a general solution, right? To our dE, which was dy dx, is equal to 2x over y. So that was a pretty simple example. Let's talk about ones that maybe involve a little more algebra. They're not always solved for dy dx, so that's generally one of the first things that you want to do is to manipulate the algebra so you have all the y's on one side and then all of the x's and the dx on the other. So let's take a look at this one. So we're given 2 plus x times y prime is equal to 3y. So, you know, I told you the very first thing you want to do, it's kind of janky, is to write y prime as dy dx. So I'm going to go ahead and do that first. Now, since the dy is in the numerator on this side, I generally will always move the y's over to that side, and then I'll move the x's to the other side. This constant 3 here can stay wherever you want it to be. You can leave it on the right-hand side and just divide by y, or you can divide by 3y. It's not going to change your answer in the end. So let's go ahead and let's move the dx and the 2 plus x over and move the 3y over. And what we end up with is dy divided by 3y, I moved the 3, is equal to dx divided by, because we have to divide both sides by 2 plus x to move it over. And then now I'm going to integrate both sides. And I find it easier if I write my integral like this, 1 over 3y dy, because you know that means the same thing, just multiply the numerators, is equal to the integral of 1 over 2 plus x dx. And so I don't have to rewrite it. You know, we always want to take our constants and pull them out front. So I'm going to erase this, and I'm going to write this as y, and then I'm going to put the 1/3 out front. So I don't have to deal with that constant. And now integrate both sides. 1 over something, 1 over something. I'm probably going to end up with some natural logs. So I end up with 1/3 the ln of the absolute value of y is equal to ln of the absolute value of 2 plus x plus c. So it's pretty simple. I mean, integrating things that you already know how to do. Now we have some kind of tricky algebra to get this thing solved for y. So in order to get rid of the ln, and I actually have an ln on both sides, I'm going to have to use my e power. So, or my e base, sorry, not power. So I want to kind of raise both sides to the e, or put the base on them. You know what I'm talking about. And I'm also going to take this 1/3 so I don't have to deal with it, and I'm going to make it an exponent on y. So what I'm going to end up with to get rid of this ln is I'm going to do e to the ln of the absolute value of y to the 1/3 power. Alright, and then this side I'm going to do e to the ln of the absolute value of 2 plus x plus c. Now some cool things happen. At least I think they're cool. Those cancel. And now let's talk about what happens to the c over here. So you know that if you have two things like this, like if you have a raised to the m power times a raised to the n, then this is a to the m plus n power. So I can kind of take this rule and work backwards, and I can change this to, and I'm not going to do this every time, so you should pay close attention, because I'm pretty much just going to do this automatically anytime it happens. And we end up with lots of ln's and e's, so we're going to do this a few times. So this is going to become e to the ln of the absolute value of 2 plus x times e raised to the c power. And then I told you that if we have a constant, you know, e raised to the c, 2 times c, we're just going to take this thing right here, and we're just going to rewrite this as c. And I'm going to put it in front. So I end up with this right here. You know that this e and the ln will cancel. So let's go ahead and do that. So I have, this was y to the 1/3. So I'm going to have y to the 1/3 is equal to c times 2 plus x. Absolute value really doesn't matter now that we are taking that the natural log is gone. So now we're going to take, and we need to get rid of the 1/3 power, so we can cube both sides. And now we'll get rid of that 1/3 power. So we end up with y is equal to c times 2 plus x cubed. And you know, c cubed is still just, we're going to rewrite it as c, so it really doesn't matter. So let's talk about particular solutions. So this obviously is a general solution. Let me finish this out really quickly. So this is going to be, let's say this, the general solution to the DE lost my pages here. Two plus x, y prime is equal to 3y is what we got up here. Y is equal to c times 2 plus x all cubed. So particular solutions, we're going to do pretty much the same thing, all the same steps that we did here, except when we get to the last step, we're going to plug in the initial condition that we're given, the point, y and x, and then take and solve for c. And we'll rewrite our solution with c replaced with whatever we find it is. And then we'll have a particular solution to the DE. So let's try another one. So let's try this right here. So we have y times y prime, oh, not equal to minus e to the x is equal to 0. And we're given the initial condition that when y is 0, when x is 0, it's equal to 4. So y of 0 is equal to 4. Alright, so let's think about what we did last time. First thing, replace y prime with dy dx. So we have y times dy dx minus e to the x is equal to 0. And then we're going to separate the variables. So I'm going to move the e to the x and the dx over to the right-hand side. Y times dy is equal to e to the x dx. And now I'm going to integrate both sides. It's pretty simple integration. And the integral of y is 1/2 y squared. And then the integral of e to the x is e to the x plus c. Alright, so now let's solve for y squared. So we're going to multiply both sides by 2. And now remember what I said, 2c is still just another constant, so we're just going to rewrite this as c. So this gives us y squared is equal to 2e to the x plus c. I could take the square root of both sides. At this point, I'm going to leave it the way it is. So I want to use my initial condition to solve for c. So I was told that when x is 0, y is 4. So I'm going to plug both of those in. So I get 4 squared is equal to 2e to the 0 plus c. So 4 squared, this is 16, is equal to 2 plus c. So then 14 is equal to c. So now I can replace c in my solution, and I end up with that my particular solution. So let's say this: the particular solution to y prime minus e to the x equal to 0 is, what do I end up with? Y squared is equal to 2e to the x plus 14. Or I could write it as this: y is equal to plus minus the square root of 2e to the x plus 14. So it's all pretty simple. I think those are all things that y'all can do very easily. So let's look at one more separation of variables. And then I have one more example that we're going to do that just involves letters. I know y'all hate those. But when we go into the application problems, logistic growth and decay, it'll be pretty helpful for us. So, you know, I can't get out of here without giving y'all one hard problem. So this is your hard problem. Y times 1 plus x squared y prime is equal to x times 1 plus, oh sorry, this should be a minus in the middle. Y squared is equal to 0. So let's start by replacing y prime with dy dx. So now I've got to figure out how I'm going to get the x's on one side and the y's on the other. So I'm going to move this thing over there. Let's try this. Y times 1 plus x squared dy dx is equal to x times 1 plus y squared. Now I'm going to divide by 1 plus x squared and 1 plus y squared and flip-flop them. And then we'll end up with pretty much the same form on both sides. I'm also in the same step going to move the dx to the right-hand side. So if I divide by 1 plus y squared and I get rid of the 1 plus x squared, I have y over 1 plus y squared dy is equal to, and then I'm going to divide by 1 plus x squared, so I have x over 1 plus x squared, and then I multiply by dx. This looks like a question you had on your test, right? You have to integrate this. We're going to use some u sub. So we have y over 1 plus y squared dy is equal to the integral of x over plus x squared dx. So I'm going to let u equal 1 plus y squared. Then du is 2y, 1/2 du, oh, I need a dy there, is equal to y dy. And I have y dy, so I'm good. I'm going to use v on the right-hand side so there's no confusion. So v is going to be the denominator, 1 plus x squared. This is pretty redundant, but dv is 2x, sorry, not 2v. Is 2x dx, and then 1/2 dv is equal to x dx. So, I mean, it's a pretty obvious substitution, I think, but maybe things that are more obvious to me aren't so obvious to y'all. So now I'm going to go ahead and plug everything in. So the y and the dy are going to cancel, right? And they're going to be replaced with du on this side and the 1/2. And then on this side, the x and the dx are going to be replaced with 1/2 dv. And then this will become v, and that will become u. A little u sub refresher. So I end up with 1/2 the integral of 1 over u du is equal to 1/2 the integral of 1 over v dv. Now integrate, so I end up with 1/2 the natural log of the absolute value of u, and I'm going to go ahead and plug u back in. U is 1 plus y squared is equal to 1/2 the natural log of the absolute value of v, and v is 1 plus x squared, and then I'm going to put the c on this side. So I have now integrated both sides. I need to solve for y. So I'm going to do that trick with the e's again that I did on the previous problem. Before I do that, I generally want to make it as simple as I can on both sides, meaning I don't want any extra constants or anything out in front of my natural logs. If I ever had more than one natural log, I'd want to put them all together. But in this case, all I want to do is I want to use my power rule for logs and make those powers instead of constants out front. So then I end up with the natural log of, I don't really need absolute values actually because everything's going to be positive. So let's do this. 1 plus y squared to the 1/2 is equal to the natural log of 1 plus x squared. If I could write x, that'd be cool. To the 1/2 plus c. So now I'm going to take both sides to the e. So I have e to the ln of 1 plus y squared to the 1/2 is equal to e to the ln of 1 plus x squared to the 1/2 plus c. And we're doing that trick again with the c. I could split up these two things on the right hand side that are added together and get e to the c as my constant. And then, you know, I can just rewrite e to the c as c. So what I end up with, I promise we're almost done, is those obviously are going to cancel, and this is just going to be 1 plus y squared to the 1/2 is equal to c times 1 plus x squared to the 1/2. Now I want to get rid of the 1/2 on the side with the y because I want to try to solve for y squared. And so I'm going to square both sides, which is cool because that'll get rid of the 1/2 on the other side. C squared is just going to be c again, so I'm going to end up with 1 plus y squared is equal to c times 1 plus x squared. And then I'm going to subtract 1 from both sides, might as well. So y squared is equal to c times 1 plus x squared minus 1. Now, I didn't give you the initial condition at the beginning of the problem, but your initial condition is that when x is 0, y is root 3. Right? Yep. So, we're going to take and we're going to plug in. So, we're going to plug in root 3 for y, and we're going to square that is equal to c times 1 plus 0 squared minus 1. This is just, let's see, this is equal to 1. So, we end up with, if we add both sides, add 1 to both sides, sorry. We end up with 3 plus 1, which is 4, is equal to c. So now I'm going to rewrite the particular solution. So let's say this, the particular solution to my d, which was y times 1 plus x squared, y prime minus x times 1 plus y squared equal to 0 is y squared is equal to 4 times 1 plus x squared minus 1, or if you like to solve it all the way for y, you can have y is equal to plus minus the square root of 4 times 1 plus x squared all minus 1. Woo! Wasn't too bad. Not too much nasty algebra. You know, sometimes the algebra can get kind of nasty, but that really wasn't so bad. So I told you I was going to do one more example where we were using variables and not, or letters and not numbers for our constants. So let's take a look at this. So we're given this dp, I guess I'm writing in red, minus kp dt is equal to 0. And we're actually given an initial condition that when x is 0, this is equal to p naught, p sub 0. So I look at this and I'm kind of confused with all the p's and the k's and all that, the t's. So what we have is we have dp dt, which means we can think of it like this. We can think of it like p is like y, and t is like x, comparing it to the previous problems that we've done. So I want to get the t on one side, the t's on one side, and the p's on the other. So I'm going to add this whole thing and move it over there. So I'm going to end up with dp is equal to kp dt. I could divide the k along with the p, but I'm probably going to leave it over there with the dt. You get the same answer both ways. It really doesn't matter. So if I move my p over here, I get dp over p is equal to k dt. K is a constant. So let's write this over here. So we know that. All right. Now I'm going to integrate both sides. Oh, somehow switched over. Oh well. And now we are going to, we're integrating. So this will be the natural log of the absolute value of p is equal to, k is just a constant, so it's like the integral of 2 or 5 or whatever. So we're just going to put a t on it. So this is going to be kt. And then we, of course, have c. Now, I have to get rid of the natural log, so I have to do my trick with the e. So I have e to the ln of the absolute value of p is equal to e to the kt plus c. Once again, e to the c, we're just going to write as c. So c will end up being a constant out front. You know, those cancel. So I'm going to end up with p is equal to c e to the kt. And now I want to use my initial condition. When x is 0, it's equal to p naught. So I'm going to plug in p naught for p is equal to ce to the k times 0. E to the 0 is just 1, so we get that p naught is equal to c. And then I get my particular solution. So the particular solution to my dE, which was dp minus kp dt equal to 0, is p is equal to p sub 0 e to the kt. If you know anything about exponential growth or decay, that should look like expression that you've seen before. So we're going to do some practice problems on these in class next time, and we're also going to do some application problems. We're going to start working on exponential growth and decay, logistic growth and decay. So that's all I've got for you today. Sorry my video wasn't so exciting, but try again next time. And I'll see y'all soon.